Dear students, after studying this module, you shall be able to know about hydroboration reactions of alkenes and alkynes. You shall be able to learn about the reagents which are used for hydroboration and identify the mechanism involved and the regio as well as stereochemistry of hydroboration. You shall be acquainted with the metal catalyzed hydroboration methods, and in this module you should be able to familiarize yourself with the synthetic applications of hydroboration products. Hydroboration refers to the addition of a hydrogen boron bond to an unsaturated system such as alkene or alkyne, resulting in the formation of organoboranes which can be converted to other products via subsequent transformations. This reaction was first explored by H.C. Brown and co-worker during 1950s. Alkenes react with borane, that is BH3, which exists as a dimer which is B2H6, and a number of its derivatives to give synthetically useful alkyl boranes. We will see all this in detail. The reaction is an electrophilic addition to alkene, but unlike other reactions, this addition is a concerted one, that is, it is a simultaneous addition. The initially formed monoalkyl borane product may undergo addition with another molecule of alkene to produce a dialkyl borane, which in turn may undergo further reaction to produce a trialkyl borane. For example, ethylene will yield triethyl borane on hydroboration. In the first step, it will be the ethyl borane formed. In the next step, the ethyl borane further reacts with the ethene to give diethyl borane, and subsequently the diethyl borane reacts with ethene and gives the triethyl borane. However, the tri-substituted alkenes usually yield a dialkyl borane, and tetra-substituted alkenes form only the monoalkyl boranes. The extent of hydroboration may also be controlled by the stoichiometry of alkene and borane. This reaction is often combined with subsequent oxidation reaction to produce an alcohol and is commonly known as hydroboration oxidation reaction. As you can see here, the alkene is first reacting with BH3, and then further subsequent treatment with hydrogen peroxide and NaOH, the boron component is getting replaced with OH. Before moving further, let us have a look on properties of borane. Borane, that is BH3, is a very reactive electrophile since it has only a sextet of electrons, that is, it has 6 electrons in its octet. Diborane gas may be generated in situ by the reaction of NaBH4 with BH3 in laboratory. But the diborane gas is highly toxic, flammable and explosive in nature, and is more conveniently handled by making its adduct with an electron donor such as tetrahydrofuran or dimethyl sulfide, etc. And these are available in solution form in an ethereal solvent, commonly THF. So, it is in this adduct form, it is more commonly used in the reaction rather than as a gas. The dimethyl sulfide complex, that is BH3 Me2X, is more stable than the BH3.THF and is soluble in a variety of organic solvents such as diethyl ether and hexane. Let us now focus on the reduction by boranes. Borane is a very reactive and is also used for reduction of a host of functional groups including aldehydes, ketones, carboxylic acids and the other functional groups such as epoxide, lactones and nitriles. Thus, on treatment with borane of alkene substrate which contain these functionalities may also cause their reduction in addition with the hydroboration reaction. Thus, easily reducible functional groups like aldehydes must be protected as their acetals, otherwise they will also get reduced. Carboxylic esters are usually tolerated, that is, they are not affected. reduction of COH to CH2OH by BH3 dot dimethyl sulfide is noteworthy. So, let us see how the hydroboration using borane derivatives is also done in addition to BH3. Sometimes the mono or dialkyl borane reagents are used for hydroboration, which are less reactive and more selective than diborane and can be used for hydroboration of less hindered alkenes. The common examples of such alkyl borane reagents include diacetyl borane, thexyl borane, 9-bora bicyclo 331 nonane, which is commonly known as 9-BBN, and catechol borane, as you can see here their structures. As we proceed further, let us try to understand the mechanism of hydroboration. In this mechanism, we have to first of all understand the nature of boron atom. Actually, as you are already aware, the boron atom is highly electrophilic because of its empty p orbital, and the pi electrons of the alkene act as a nucleophile to attack the electrophilic boron atoms. However, the reaction is a concerted process, and what we mean by concerted process is that the entire BH3 molecule will be adding to the alkene carbon-carbon double bond simultaneously. It is not going to happen part by part, unlike the other electrophilic additions you have seen, where the electrophile attacks first, you get the intermediate carbocation and then the nucleophile attacks. Here the entire BH3 molecule is going to attack simultaneously, and that is what is called as a concerted process. So, the reaction is a concerted process and no carbocation type intermediate has ever been isolated. A 4-member transition state is involved here, in which the breaking of BH bonds and making of CH bonds all take place simultaneously, as you can see here for the case of hydroboration of methyl cyclohexene. And this ultimately results in the addition of H and BH2 to the place where there was a carbon-carbon double bond, as is clear from this structure. Another thing to notice here in this mechanism is that because the H and BH2 components are simultaneously adding, so they are both coming from the same side of the molecule. That is, if we talk in terms of stereochemistry of this reaction, it is a syn addition. Another thing to notice here is that the addition of H and BH2 happens in such a way that the BH2 components adds to the carbon which is less substituted, and H goes to the carbon which is more substituted. So, the most favored transition state is as shown here and not other way round, which would have led to the formation of BH2 addition on a more substituted carbon. Let us understand this in more detail, that how the hydroboration results in anti-Markovnikov addition product. The reaction results in anti-Markovnikov product, that is, the hydrogen adds to the more substituted carbon of the double bond. This regiochemistry is the reverse of a typical HX addition to the alkene, which is a result of the polarity of the BH bond. Actually, the BH bonds in diborane is polarized as B positive H negative, unlike the HX where H is positive and X is negative, and this is due to the electronegativity difference between the boron and hydrogen atom, and you know the boron is more electropositive, so it bears the positive charge and hydrogen in turn bears the negative. So, you can say the BH3 is actually a hydride donor. It is providing the H minus, and the remaining BH2 from the entire BH3 is having a positive charge. So, that is the reason why the BH2 attacks in a manner that there is a more character of carbocation which is more stable, that is a more substituted one. As the addition of the empty p orbital to the less substituted end of the alkene gets underway, a hydrogen atom from the boron adds with its pair of electrons to the carbon atom which is becoming positively charged. Thus, the addition is a syn addition. And recall, I have told you earlier also, because of both the parts adding from same side of the molecule, it is syn addition. It is not happening that one group is coming from one side and the other is coming from other, in which case it would have given you anti-addition. So, it is not the anti-addition, but it is the syn addition. The formation of Cb bond is slightly faster than that of the CH bond, but still it is concerted, so that the boron and carbon are partially charged in the 4-centered transition state. The developing positive charge is present on the more substituted carbon analogous to a stable carbocation, and hence the reaction proceeds via anti-Markovnikov regiochemistry. Due to the syn addition of the boron and hydrogen atom, the reaction is highly stereoselective, with the hydroboration taking place preferentially on the less hindered side of the double bond, as shown for 1-methyl cyclopentene. So, in this example of 1-methyl cyclopentene, you can see as the BH3 adds and with 2 more 1-methyl cyclopentyl groups, you have the Br2 adding and H adding, and notice that the Br2 and H are on the same side, and subsequently if you do its oxidation, that is the reaction with hydrogen peroxide in the presence of base, this Br2 is going to be replaced by OH. So, both the H and OH will be adding syn manner, that is on the same side of this cyclopentane molecule. Let us now move to how the steric effects, they also explain the regiochemistry and stereochemistry of hydroboration. Another explanation for the anti-Markovnikov regiochemistry of hydroboration is the steric effect of boron containing group, which is much bulkier than the hydrogen atom, and hence it is very obvious that the boron gets attached to the less hindered end of the double bond and not other way round. The selectivity of the first addition of boron is relatively low, but the steric effect is more pronounced in the second or third successive hydroboration, and hence the anti-Markovnikov selectivity may predominate in the end. With most substituted alkenes, the reaction stops at second hydroboration, as third hydroboration becomes quite difficult due to the increased steric strain. However, it must be noted that the borane itself may not give good regioselectivity, as it is highly reactive and does not have enough steric bulk. The steric effect is more pronounced in the sterically congested alkyl borane reagents like the 9-BBN, which are also less reactive than borane and lead to enhanced regioselectivity. Now, this we can take an example, that is the case of hydroboration of 4-methyl pent-2-ene by the various reagents. So, in this case of 2-methyl pent-2-ene, when it is reacted by various boron reagents, you can see as we are moving from BH3, which is sterically less hindered, to di-isoamyl borane, which is sterically more hindered, and 9-BBN, which is even sterically more bigger molecule, the percentage of the two products is shifting exclusively to the left one, where it is in the anti-Markovnikov manner. You can see here with BH3 it is 57% of the first product and 43% of the second. So, second also is quite in a predominant amount, and as you go from diacetyl borane to 9-BBN, the percentage varies and you get 97:3% for diacetyl borane and you get 99.8% the exclusive anti-Markovnikov addition product in case of 9-BBN. So, this actually is enforcing and clearly telling you that steric effects are quite important in deciding and taking the role of the addition of reagent in such a manner which is anti-Markovnikov. So, to sum up, we can say in this example The sterically congested alkyl borane, that is 9-BVN etc., show extremely good stereoselectivities in bicyclic systems where the attack of 9-BVN occurs from the less hindered side, as exemplified also by the Nor-Bornyl system we will be showing right now. So, in this Nor-Bornyl system also you can clearly see, if you take the reagent for hydroboration as BH3 followed by oxidation, the out of endo and exo product, the exo product is 87% and endo product is still there as 13%. But as you move to 9-BVN, which is sterically a bigger reagent, then the exo is exclusively almost 99.5% and endo has reduced to only marginal 0.5%. Now let us try to see what will happen if we take haloboranes rather than BH3. Haloboranes like BH2Cl, BH2Br, BHCl2 and BHBr2 are also used as hydroborating reagents. These compounds show similar reactivity as borane, but they are somewhat more regioselective than borane. Also, after hydroboration, the halogen atom can be replaced by a hydride and subsequent hydroboration can be carried out to them, and thereby one can prepare the unsymmetrical alkyl boranes. As you can see here, starting with propene, if you add BH2Cl, two of the alkene units are joining, that is wherever you have the two hydrogens they are getting replaced with this, and this on further reduction with lithium aluminum hydride, the Cl gets reduced to H. So, you get a trialkyl borane, and this you can now add a different alkene and you can get a trialkyl borane which is unsymmetrical trialkyl borane. Let us now move to what are the other factors which influence the mechanism of hydroboration. In many cases, the presence of electronegative substituents at the gamma position of the alkene leads to an altered and sometimes reversed regiochemistry. Also, there is often a reduction in the rate of reaction. This has been attributed to the cumulative electronic effects, that is the inductive and mesomeric effects of the electron withdrawing groups present. As you can see in these two cases also, when you have the substituent OET, that is the alkoxy, then the percentage of attack, it is 81% at the terminal carbon. On the other hand, when you have the chlorine substituent which is more electron withdrawing, in that case the percentage of attack at the terminal carbon reduces from 81% in OET case to 60% here, and to the substituted carbon the attack has now increased considerably. Similar effects when observed with oxygen containing substrates such as ethers, alcohol, esters etc. A term, that is oxygen directed hydroboration, has been used in literature for these observed effects. Now, this can be theoretically attributed to a Lewis base interaction that leads to an oxygen borane complex. An olefin tethered to the boron complex oxygen then forms a complex to the borane, and finally hydroboration occurs by the addition of a BH bond to the CC double bond. Now, you can see here in this example, at one end there is a OR group and at the other end you have the alkene double bond. Now, this when it is reacted with BH3, it first of all the BH3 forms the complex, the oxygen boron complex at the OR end, and then from this it is ultimately transferred or tethered to the alkene, and finally it rearranges itself to have the BH2 and H. For the sterically congested alkyl borane reagents, the terminal alkynes have been found to react more rapidly than internal alkenes. Similarly, Z alkenes react more rapidly than E alkenes. Let us now understand how the metal catalyzed hydroboration takes place. During 1980s, it was found that Wilkinson's catalyst can catalyze the hydroboration of olefins with catechol borane. catechol borane has two boron oxygen bonds and is much less reactive as a hydroborating agent. Now, without a catalyst, such reactions require elevated temperatures, but with the help of catalyst, the reaction can be performed at room temperature or below. Even in some cases, iridium-1 catalysts have been reported. Now, let us try to understand this with the help of an example. As you can see here, 1-hexene, when it is treated with this catechol borane and then later on oxidized with H2O2 in the presence of NaOH, we get this corresponding alcohol. But in this reaction, notice that the temperature required is very high, that is 90 degrees centigrade. On the other hand, if the same reaction is performed with the hydroborating agent as catechol borane, but in the presence of Wilkinson's catalyst, then we require only room temperature, and that too within 5 minutes we get the hydroboration. And this subsequently, when it is treated with H2O2 and NaOH, we get this alcohol. So it is the same product, but notice that when you are using catalyst, you require very mild conditions, room temperature, but when you are not using catalyst, then we require very high temperature. Let us now try to understand how the metal catalyzed hydroboration takes place when we take Wilkinson catalyst. And Wilkinson catalyst can catalyze the hydroboration of olefins with catechol borane. The mechanism of the rhodium-1 catalyzed hydroboration is different and occurs via the classic iterative cycle of metal catalyzed cross couplings. In this reaction mechanism, as you can see here, the first step is the removal of triphosphene moiety with the solvent. In this step, neither the oxidation step nor total electron count gets changed. In the next step, there is oxidative addition of catechol borane. So, the coordination number and the oxidation state of the central metal ion, that is rhodium, increases by 2 units, and the catechol borane moiety adds in the form of alkyl part, that is BRO twice and H. After this, there is addition of alkene in place of solvent moiety. And after this step, migratory insertion of hydrogen occurs. Now the alkene is converted to alkane in this step. And this is the slowest step, therefore it is the rate determining step of this reaction cycle. Further on, there is a reductive elimination of the boron and the alkane part which occurs, resulting in the formation of this alkyl borane, which you are already aware can lead to many different products on treatment with different reagents. And after this step, the catalyst can be regenerated very easily, as you can see, and that is why it is a cyclic mechanism, or we can say it is the classic iterative cycle of metal catalyzed cross coupling which takes place. Let us now look at the synthetic applications of hydroboration. First of them is the oxidation to alcohols. As mentioned earlier also, organoboranes can be converted to an alcohol on reaction with alkaline hydrogen peroxide solution. That is, what you have to do is, you start with an alkene, react with BH3 or its dimer B2H6, that is, you have already studied is the hydroboration step, where you will be first getting a monoalkyl borane or a di or tri, and this subsequently on oxidation, that is treatment with H2O2 in the presence of NaOH, you will get OH. Notice that the OH is coming just in place of the BH2 in the very first step that you are getting. And if you look at the overall H and OH addition, that will be anti-Markovnikov. The mechanism of the oxidation step, that is the treatment of alkyl borane with hydrogen peroxide and NaOH, involves the nucleophilic attack of hydroperoxide ion, that is OOH minus, with R3B, which is a Lewis acid, followed by a subsequent 1,2 alkyl shift displacing a hydroxide ion. These two steps are repeated 2 or more times to generate finally a trialkyl borate, that is BOR thrice. The nucleophilic hydroxide anion then attacks the boron atom and an alkoxide ion is eliminated. Protonation of the alkoxide ion then subsequently forms the alcohol. These 3 steps are repeated 2 times to yield finally the 3 molecules of the desired alcohol from the tri-substituted borane. The oxidation reaction proceeds with retention of configuration, that is, the stereochemistry is retained here. This protonolysis is a chemical method of reduction of a double bond and is a good alternative to catalytic hydrogenation. Another importance of this reaction is that we can use it to introduce the deuterium. When you use deuterium in place of hydrogen in carboxylic acid, we can do that. Let us see with the help of an example how we can do. So, starting with 1-methyl cyclohexene, when we do the hydroboration using 9-BBN, and subsequently if we do the reaction with CH3COOD, that is the deuterated acetic acid, then we can have deuterium in place of boron. Coming to another synthetic application of hydroboration, we can use it for preparation of amines, that is the conversion of alkenes into amines. Similar to the oxidation with hydroperoxide of organoboranes, treatment with hydroxylamine O-sulfonic acid, that is NH2OSO3H, yields an adduct in which migration of an alkyl group to nitrogen occurs and the resulting amine borane salt on hydrolyzing with water yields the amine salt, which can be neutralized with the base to get free amine. However, not all 3 alkyl groups migrate, and usually the methyl groups attached to boron resist migration. Hence, this methodology can be used to generate amines on alkenes by using dimethyl as a hydroboration reagent and its subsequent amination. So, as you can see in this example of 1-methyl cyclohexene, in the first step when hydroboration happens, you have the addition of H and BH2. Notice that H and BH2 have added from the same side, that is the syn addition, and this subsequently followed by amination. The BH2 is then replaced by NH2. Let us now study about the carbonylation of organoboranes. Treatment of organoboranes with carbon monoxide in a pressure reactor leads to the formation of Lewis acid base complex, and these adducts undergo boron to carbon migration. By carefully manipulating the reaction conditions, a range of products, for example alcohols which can be primary, secondary or tertiary, aldehydes and ketones can be obtained, as we will be discussing now. For getting aldehydes, the carbonylation is done in the presence of a reducing agent such as lithium trimethoxy aluminium hydride, which leads to only one boron to carbon migration, and resulting oxidation yields the aldehyde. Let us see this mechanism, how it happens. As you can see that this trialkyl borane gets reacted with carbon monoxide, and you are already aware that boron is a Lewis acid and carbon monoxide through the carbon will be transferring this electron pair, and as a result you get this adduct. In this adduct, this alkyl group gets migrated to the electron deficient carbon, and furthermore there is another alkyl group and rearrangement which happens, and it leads to the formation of this epoxide. Now, it is this epoxide which further undergoes rearrangement to give this boron oxide, and which further on treatment with H2O2 in the presence of alkaline medium will give the corresponding alcohol. So, you can clearly see that BO is getting replaced with this OH, and depending upon the nature of R, you can either prepare a primary or a secondary or a tertiary alcohol. If this epoxide that we had got is treated with water, that is it undergoes hydration, it will add water and as a result you get this diol. This resulting diol further on treatment with base gives the alcohol. You can clearly see here in this case this boron part has been replaced by H and you get this resulting alcohol. On the other hand, if you do the treatment with OOH minus, that is the perhydroxide, then what happens is this boron part gets replaced with OH and these two OH undergo dehydration as they are on the same carbon and you get the resulting carbonyl compound. Now moving further to the hydroboration of alkynes. Just very similar to the alkenes, the hydroboration happens on alkynes, but they on further treatment will give you different products. Let us see in detail. Hydroboration of alkynes takes place in a similar way as that of the alkene substrates, wherein 3 moles of the alkyne react with 1 mole of boron trisubstituted alkene. This alkynyl borane can also undergo a host of reactions as the alkyl boranes and hence can be converted to a variety of useful products. Let us consider an example, which is the protonolysis of the alkynyl boranes. It can lead to alkenes in good yield. So, as a result what you can do is you can convert the alkynes into alkenes. Let us try to understand this with the help of this equation. Now, you can see here the 3 moles of this alkyne, when they react with BH3, the BH3 adds to the triple bond and H adds to one carbon, the BH2 adds to the other carbon. And this treatment with 2 more alkyne molecules, you will ultimately have this trialkyl or better the trialkenyl borane. When this is further treated with acetic acid, what happens is, notice that this boron will get replaced with hydrogen and you get 3 moles of this alkenes. And one very important thing to notice here is, like the earlier cases, the addition of BH3 is via the 4-member transition state and that is why it is the syn addition. So, notice you will be getting the cis alkene as a result and not the trans alkene. Moving further, the alkyne hydroboration oxidation strategy does not yield an alcohol like the alkenes. Rather, the resulting is an enol which tautomerizes to form a ketone. Let us understand this with the help of this equation. So, in this general equation you can see that when 3 moles of any alkyne are react with BH3, there will be addition of H and BH2 and subsequently you get this trialkenyl borane, and this when it is further treated with H2O2 in the presence of NaOH, it undergoes hydrolysis and this boron part gets replaced with OH. So, this resulting enol, as you are already aware, will tautomerize to the corresponding carbonyl compound. So, here in this case what you are getting is a ketone which is the product. The alkenyl boranes may also further react with borane, leading to a mixture of products. With di-substituted alkyne, this is not much of a problem, but with terminal alkynes, the hydroboration proceeds further, leading to a mixture of alkyl and alkenyl boranes. To avoid this, bulkier di-substituted boranes like dicyl borane, thexyl borane, etc. are used as discussed earlier. So, here also we can have the similar applications of these bulkier di-substituted boranes. Let us now summarize what we have learnt in this module. We have learnt that hydroboration refers to the addition of a hydrogen boron bond to an unsaturated system which can be alkene or alkyne, and it results in the formation of organoboranes which can be converted to variety of other products via the subsequent transformations. We have also studied that hydroboration is highly regioselective and syn stereospecific process and results in anti-Markovnikov addition. And if we talk about the mechanism, a concerted 4-centered mechanism has been proposed, which we have discussed in detail. Borane, that is BH3, is commonly employed either as its dimeric gaseous form or as adduct, that is B2H6 with THF or DMS. Boron, that is BH3, is commonly employed either as its dimeric gaseous form, that is B2H6, or as adduct with THF or DMS. A wide variety of organoborane reagents are also available for hydroboration, which are less reactive and more selective. The number of hydrogen substituents on the borane determines the number of olefins with which it can react. The rate of hydroboration is strongly affected by the substituents on the boron atom. Sterically bulky substituents can appreciably reduce the rate of successive hydroboration reaction and improve the regio and stereo selectivity of the reaction. We had also learned that the sp3 hybridized carbon boron bonds can be manipulated in a number of ways, including oxidation, amination, carbonylation and other variety of synthetically useful transformation. We also studied the hydroboration of alkynes, which occurs in a very similar way to that of alkene, but to stop the reaction at alkene stage, the disubstituted borane reagents are employed.